Hello, students. Welcome back. In our last video, we have seen what is an algorithm and how to analyze various possible solutions for a given problem. We have seen some examples in our last video lecture. We have talked about the asymptotic analysis of an algorithm. We talked about the big O, big theta, and big omega notations. So just to summarize the previous lecture, that what actually is the analysis of the time efficiency of an algorithm is the time efficiency of an is analyzed by determining the number of repetitions that what we were doing. I mean, we were checking the loops, that how many times it is being repeated. What we are checking, the basic operation. What do we mean by the basic operation? Basic operation is the operation, any arithmetic operation, comparison operation, logical operation, whatever is the operation, is the operation which usually operates maximum amount of the time, most of the time, and that is usually in the innermost loop, right? Usually in the innermost loop. If we have the multiple loops, in the innermost loop, whatever we are performing is normally considered as the basic operation, and we have to actually find it with respect from a function with respect to the input size. So what we were doing here is we were actually computing a function like t of n, which is actually equivalent to some c of n or f of n. In last example we have seen that, where this t of n is the running time, t is the running time, where n is the input size that we have seen, right? And on the right hand side, which we were getting, like for example, in our previous video, we have find out f of n is equal to something like 4n square plus 8n plus 4, something like this one, right? So this is basically f of n or t of n, whatever you want to say. This is the time taken by the algorithm. This is the size of the input. And here, whatever we are going to get on the right hand side is something. Let me take one term only, 4n square, for example. This 4 is how many time, or how many time the operation is, what is the cost to execute that operation. And then this n squared tells me that how many time this operation is being executed, being repeated. So that's what we are going to say here. This is the cost of the operation, and this is how many time this operation is being performed. And we multiply them, and then we sum all the multiplications to form this function. That's what we have done in our last class. Now, today, of course, we are going to do more practice about that. So we have seen the asymptotic growth. One was the big O of n, big O of f of n, which is basically the class of function for t of n that says my function t of n will grow no more than this f of n, which is the upper bound. Remember, this was the upper bound for our functions, right? Upper bound, which we were saying the worst case, that this is the maximum, this can grow no more than this. The omega of n is the function for t of n, which means it grows at least for f of n. This is the lower limit or lower bound, that this has to grow minimum this amount of time. This has to take time, at least minimum time, which is this one. Whereas theta is a tight bound, and we say that the tight bound, which is between the upper bound and the lower bound, so that grows as same as f of n. This is the in between f of n, the function between two limits, the upper limit and the lower limit. Okay, that's the same thing that we have seen, that the worst case is the maximum number of time that this has to execute. The best case is the minimum number of time that it has to execute. The average case is, on average, how much the algorithm behaves, how many times this has to execute on average. Remember, this is not the average of the worst and the best case. It is the average, that on average, how much time this algorithm takes to execute, to solve a problem. Now, we have some important efficiency classes whenever we are going to compute a function like this one, like we have computed here. If this is the function t of n or f of n, we have computed. Now, this function will lie in one of the efficiency classes, like for example the constant class, which is the best class. Like we have find out in our last video, t of n is equal to, for example, 3, which is the constant that does not involve any variable. The logarithmic class, which is also best after the constant, something like this one, t of n is equal to log of n, for example, and plus some more constant and something else. We will ignore the constant. Why? We will just discuss it. We will discuss it in short time. The next class is called the linear class. For example, t of n is equal to 5n plus 3, right? Something like this one, which is the linear. The order of growth of the function with respect to the input n is growth is linear. The next one is a linear logarithmic, like this one. T of n is equal to, for example, 5n log n plus 9, something like this one. The next class is called the quadratic class, which is something like this one. For example, 6n squared plus 4n plus 3. Right, where we have the higher order polynomial is a square polynomial, which is the quadratic. The next is the cubic. The same, like the higher polynomial would be the cubic one, like for example 9n cube plus 6n square plus 2n plus 5, whatever, something like this one, any random equation. I'm just computing it. So the higher order polynomial is a cubic one, so we call it the cubic class. The next is the exponential class. Exponential class is not the good one, it's the worst one. So an algorithm can take the worst time as an exponential, like for example, if it goes to the 2 to the power of n, or 3 to the power of n, or 5 to the power of n, whatever it is, right? So the input size is on the exponent, which is the worst. And then the most, even then after that, this becomes the n factorial, where we are going to get something like 5n factorial plus 2n and so on whatsoever. So the higher order polynomial is a factorial. So these are the efficiency classes. If an algorithm performs in a constant amount of time, or a logarithmic time, or a linear time, we call it the best algorithm, the best known algorithm, right? So we will definitely opt the algorithm if they falls into this class, or even if they fall in the linear logarithmic class or in the quadratic class, we will say that, okay, this algorithm is good, right? It is good algorithm, so we will choose this. But if it falls in the cubic, is okay, we still can use it, but it is actually the growth is cubic, means if the input is for example, if you are going to sort 2 elements, it will take 2 to the power of 3. But if you are going to compute the sort the 5 lists, take 5 to the power of 3, which is, I mean, too much. We can still use it, but it's, and these are the actually not good, right? Not good, but these classes still exist. There are many problems that you cannot solve in the without the exponential or the factorial time, that we shall see in one of the example later on. But these are the common classes, efficiency classes. So whenever we are going to compute the efficiency of an algorithm, I mean, computing the efficiency means we are going to compute the function t of n or f of n, whatever we can say it. So these function will actually fall in one of the classes that we have listed over here. And now when we have the class like this one, let's say, for example, let me take the example of this one, right? So if we have this one, we only consider the higher order polynomial and we ignore rest of that. If we are talking about big O, which is the worst case, and if that case, I will say, hey, this belongs to the n square, right? This is the O of n square. This belongs to O of n cube. This is O of 2 power n. That means whenever we are going to write in terms of big O, big theta, or big omega, we only, specifically I'm talking about big O now. When big O, when we consider, we write the function in terms of big O, we will only consider the higher order polynomial and we will ignore rest of the thing. The reason why we are taking this is because the higher order polynomial is the important element which contributes in the growth of the function, right? That how my function is growing depends on the higher order polynomial. So we'll take that and we'll ignore rest of the elements, right? Okay, now what happens is when we are going to analyze the algorithm, algorithms are basically of two types, right? So in general, there are of two types of algorithms that we have seen already in programming. One is called the recursive algorithm, where when we talk about the recursive, I mean these are the loops, for, while, do, while, and so on. And the other one, the recursive algorithms are the algorithm that involves recursion. So let me call non-recursive algorithm, and the other one is the recursive. Right? So non-recursive algorithms are the looping algorithms. Recursive involve recursion. they both are different in terms of analyzing them. When we are going to analyze the algorithms, they both are different. They both have different ways. So in this video, I'm focusing myself in analyzing the non-recursive algorithm. In the next video, we shall talk about the recursive algorithm, how to analyze the recursive algorithm. So if we have given with a non-recursive algorithm, which involve loops, so what is the way to analyze it? First of all, we shall see what is the input size. We will determine the input size. For example, if you are going to sort the list, the input size is the number of elements. If you are going to search an element from the list, the size of the input, of course, is the number of elements that you have to look for. If, for example, you are going to compute something else, I mean, depending on, for example, if you are going to add two matrices, then the input size is the dimension of those matrices, right? So different problem have the different input size that we have to first of all find out. The next thing that we have to identify is the basic operation. What is the basic operation being performed in this algorithm? And as I said, it is the operation which is in the innermost loop. And then we shall find out, determine the worst case, average case, and the best case of these algorithms. Most of the time, we shall only discuss about the worst case in our programs, in our classes. And then this is the important step. We will set up the sum equation. The sum equation is important because we need to count how many times this basic operation is being computed. And the mathematical way of counting something is to formulate a sum equation, to set up the sum equation. How to do so? Obviously, we will do with some examples in the coming class. And then once we have set up the sum equation, we will solve that sum equation, we'll simplify it using the standard formulas. What are those standard formulas is given here? Like, for example, if you are giving with a sum equation like this one, I is going to start from 1 to n, right? So, for example, this one, right? And there is one operation being performed. And you can actually represent it either with C or 1. That means the constant, right? So whenever we are going to use 1 means something constant. And then this means it's nothing but it's basically sum of the numbers for n times. 1 plus 1 plus 1 plus 1 up to n times, right? And we can simplify it with the help of simply the upper limit, which is n, minus the lower limit, which is 1. The lower limit is 1, plus 1 from the formula, which is going to be n. So we'll simply say this belongs to O of n, right? That's, I just explained the first one. I am not going to explain the rest of the others. You can pause the video and you can solve rest of the. Okay, let me just say one more. For example, I is going to start from 1 to n, right? This one, right? And you are going to have I here. And I is something where repetition is involved. So this is basically going to be 1. I mean, you are going to add first n number 1, 2, 3, 4, 5, 6 up to n. So this involves n into n plus 1 divided by 2. This is how we are going to solve it. This is going to be n square plus n divided by 2, right? N square plus n divided by 2. And when I write it in terms of big O, I will only consider the higher order polynomial and I will say, hey, this is O of n square. And you can now solve rest of that. And you can refer the book that how these summations are being solved, right? With this understanding, let's write some algorithm and then we are going to do the same thing. I mean, we will find out the basic operation, we'll set up the sum equation, and then we are going to solve the sum equation using these formulas, and then we shall see what is the efficiency of the algorithm, or in which efficiency class this algorithm falls. So I'm going to take very simple algorithms for our understanding, right? For example, this is an algorithm A, which has one loop and it performs some operation. So first thing, what is the basic operation? Of course, the operation that is being executed most of the time, which is being performed most of the time, is the basic operation. So in this case, this print is being executed most of the time. So this is my basic operation, right? This is the basic operation. And now what I have to do next is I have to set up the sum equation so that I can evaluate it. How to set up the sum equation is simple. So you will simply say the sum sign from where this loop is going to start. It's going to start from 1. So I'm going to say, hey, I is equal to 1. Up till when this loop is going to run up to n. So I'm going to run n times. And what I'm going to do in this loop is this basic operation, which is a constant amount of work. What is the constant amount of work? I have to print something on the screen or in the file or whatever. So whatever it is, every time it takes the constant time. So which is 1. So I'm going to say 1, right? And now This is how I have set up the sum equation. The next step is to solve this sum equation. How to solve this sum equation is now simple. So once we have set up this sum equation, we have to solve it. How to solve it? Since this is the first class, so which is the upper limit minus the lower limit plus 1. So that we have to do. So upper limit here is n, lower limit here is 1. So n minus 1 plus 1 from the formula, right? 1 from the formula. So minus 1 and plus 1 is cancelled out. I can simply say that this belongs to O of n. This is a linear class. This algorithm performs linearly. So it depends entirely on the n. Whatever is the size of the n, the loop has to run that time. So this is n O of n. Okay, let's take one more example. So this here we have two loops, right? So the basic operation, of course, the basic operation is the same, which is the innermost loop, the operation performed in the innermost loop, which is to print welcome once again. Now, how to set up the sum equations? That is the important point here. So you will set up the sum equation for the outer loop first, so which is going to start from, I is going to start from 1 up to n, right? And inside this loop, we have another loop. So that means we are going to have one more sum equation here, where j is going to start from 1, j is going to start from 1 up to n once again. And what is happening here is a statement which takes constant amount of time, which is 1, right? So we have set up this sum equation. Now we will solve this equation. How to solve this equation is simple again. First of all, we will solve the inner equation, right? Inner summation. So outer summation remains same. I is going to 1 to n. The inner summation is going to be simple now because it's the constant amount. So that is upper limit minus lower limit. So upper limit is n minus lower limit, which is 1, plus 1 from the formula, which is we have seen in our previous slide as well. So 1 and 1 is cancelled out. Then what remaining is the n. So if I simplify this, is going to be summation I is going to be 1 to n, right? Now, one thing that you should note here, this n is a constant with respect to this I, because repetition is starting from with respect to I, starting from I is equal to 1 to n. So whatever this variable is, which is n, is constant. So I can move this n outside the summation because we do not apply summation on the constants. So I is going to be 1 to n. Whatever remaining is n, 1 now, right? And now I can solve this one. I can solve this summation as well. So how to solve this one? The simple one, n is outside. And now here, the upper limit, which is n, the lower limit, which is 1 again, minus 1, plus the 1 from the formula, right? Like this one. Now, this 1 and 1 is cancelled out. The remaining stuff is n into n, which is n square, right? So I can say that this algorithm is big O of n square, which is quadratic one. So this algorithm will take, in a worst case, whatever is the value of the n, it will take to the n square time to compute the the maximum time to print welcome on the screen, right? Okay, let's take one more example. In this example, we are now having 3 loops. So we shall again do the same thing. We will set up the sum equation. How to set up the sum equation? Let's first set up the sum equation for the outer loop. So the outer loop is going to be I is going to start from 1, is going to run up till n time. Then the next, what we are doing in the outer loop, we have another loop. So we'll set up another sum equation inside this one, which is j is going to start from 1 to n. What we are doing in this loop, we have another loop inside this loop. That means another sum equation. So 3 sum equations. K is going to start from 1 up to n. And what we are doing here in this loop, we are printing welcome on the screen, which takes a constant amount of time, which is 1. So 1 here. So we are able to set up the sum equation. Now what's next? Next is to solve this equation. How to solve this equation? So we'll first solve the innermost sum equation, and then we shall solve the next sum equation, and then the next one. So that means we are going to solve the outer 2 equations will be same. I is equal to 1 to n. J start from 1 to n. The inner sum equation is going to be now the upper limit, which is n, the lower limit, which is 1, plus 1 from the formula. 1 and 1 is cancelled out, so n is remaining. So what remaining is now would be summation I start from 1 to n, summation j starts from 1 to n, and the remaining stuff is n only. And the same thing now, this n is constant with respect to this j. So let's move this n out of this j summation. Then we move it out, it will become here at this point. And then this n is also constant with respect to this I. So let's move this n outside both of these summations. So n times summation I is going to start from 1 to n. Summation j starts from 1 to n. Whatever remaining is only 1 once again, because n is multiplied with 1 if you take n out. So 1 is remaining there. Okay. So, okay. Now, next we have to solve this sum equation, right? So let's solve this one now. So n is there, summation j is, okay, I starts from 1 to n is there, right? And now we are going to solve this one, which is n minus lower limit, which is 1 plus 1 from the formula. Again, 1 and 1 is cancelled out. Remaining stuff is n. So let me just write it over here. N times summation I is going to start from 1 to n. The remaining is n. And now this n is constant with respect to this side. Let me move this n outside. So when I move this n outside, n will be multiplied with n, which is going to make it n square. And summation I starts from 1 to n, and the remaining is 1 only. What's next? Now I have to solve this summation. So which is going to be n square into this. When we solve this sum equation now is going to be the upper limit, which is n. This is the upper limit, right? So minus lower limit, which is 1 plus 1 from the formula. So 1 and 1 is cancelled out. What remaining is n. So n square times n is going to be n cubed. So this algorithm, in a worst case, performs big O of n cube time. It takes n cube time. That is how we are going to analyze the algorithm. Now, one thing that you should notice from here, up till this point, what we have done is when there is one loop only, the algorithm is going to be a linear, take a linear time, which is O of n. When we have two loops, one nested loop, so the algorithm is going to take O of n square. And then we were having three loops now, three nested loops. It's going to take O of n cube time. Now you can deduce that. If there are 4 loops, it's n4. There are 5 loops, it's n to the power of 5. There are 5 loops, it's 6 loops to n to the power of 6. Depending on whatever this depends on the nested loops. How many nested loops are there? Based on that, we have to find it. But then most of the time it is true. It is not true always. That is why we have to go scientifically and we have to figure it out. We shall see in some examples that this is not true in some cases. Now let's solve this one more example. So first of all, set up the sum equation. So set up the sum equation means something is different here. Like for example, I is going to start from 1, then I am saying I square is less than n, which is different than the normal scenario that we have been seeing, which will create a trouble for me. But I can always rewrite it like this one. You can see that I is less than or equal to square root of n. Now it is easy for me, right? So because I is the iterative variable, so now I can set up the sum equation, which is going to be I is going to start from 1 to square root of n. And what I am performing here is a constant amount of work, which is printing that takes 1 unit of time. Now I can solve this sum equation simply. The upper limit, which is the square root of n, minus lower limit, which is 1 plus 1 from the formula. And this is cancelled out. I can simply say now, this algorithm will take square root of n time in a worst case, which is big O of n, square root of n, right? Let's take 2 more examples. Let's say this one. So this algorithm again has 3 loops, but see how we can formulate the sum equation and how we can solve it. Let's say, for example, now, first of all, the outer loop is going to be, let's set up it for the outer loop, right? Okay, the outer loop is going to run for, let's say, let me set up over here, summation I is going to start from 1 to n, right? What I am going to, in the outer loop, we have another loop in the outer loop. So that means another sum equation, which is going to be j is going to start from 1 to I. So because this is not a constant, now it is running for I times, which is different than the previous one. So in the previous, we were having n here, right? There, this time we are having I. Next, what we are doing in this loop is we are having another loop, which is going to be summation, one more summation, which is going to be k starts from 1, but this k is running for a constant amount of time, which is up to 100. So 100 here. right? And what we are doing in this loop is, this is the basic operation, which is in the innermost loop, which is to print welcome, which takes a constant amount of time, which is 1. So we are able to set up this sum equation, which is step number 1. Now we have to solve this summation. So how to solve this one? Obviously, we are going to solve the innermost first, this innermost sum equation first. So I'm going to say, hey, I is going to start from 1 to n, which is same. J is going to start from 1 to I. And now I have to solve this one, which is upper limit. Upper limit is 100 minus lower limit, which is 1 plus 1. So 1 and 1 is cancelled out, which is 100 now. So 100 is a constant value with respect to J. So we'll move 100 out of J. And 100 is also constant with respect to I. So I will move 100 out from I as well. So 100, I is going to start from 1 to n. J is going to start from 1 to I. And then what is remaining is 1 only, right? So 1 is remaining inside this summation. Now we have to solve this one. Now let's solve this summation, inner summation as well. Now let's see how we can solve it. So I'm going to say, hey, 100, I is going to start from 1 to n. The upper limit is I, right? Minus the lower limit, which is 1 plus 1 from the formula. So that means this 1 and 1 is cancelled out once again. Remaining is I. So whatever is remaining is I. Now let me just rewrite it so that we can solve it once again. I is going to start from 1 to n I. So this I is not constant with respect to this I. This is a variable. So that means this is something we cannot move out of the summation now. If this is the scenario, what we have to do? We have a summation formula for that. If you go back, let's go back to the summations formula, which is here. If you are going to get an I over here, which is this one, right? Which is this, that means whatever is the upper limit, which is n into n plus 1 divided by 2 would be the formula. So we'll replace this summation with this formula, right? So let me just go back now to the summation. And now what I'm going to do is I'm going to say, hey, 100 is there. But now this summation is being replaced with n plus n into n plus 1 divided by 2, right? That's how we are going to write it. So pause this, make a note of the sum equations, some formulas, and you can verify it. Now I can simplify this to, we'll cancel out this to the 50, which is going to be 50 times, it's going to be n square plus n. So if you simplify this, it's going to be 50n square plus 50n. And now when we talk about the big O, we only consider the higher order polynomial. The higher order polynomial is n square, and we ignore all the constants. So we can say that this is big O of n square. So remember, a few minutes ago, I made a claim that if there are 3 inner loops, it's going to be the n cube. But then here, there were 3 loops, it's going to be the n square. That means we have to be careful while making a decision whether it belongs to the cubic class or to the quadratic class. We have to solve it to find the accurate answer. So if you get the answer question, such type of questions in the exam, be careful, solve it first, and then you will be able to find the correct answer. So this is going to start from k is equal to 1 to, it's going to run until n by 2. So it's n by 2. So this is how we are going to do that, right? And what we are performing here is a constant operation inside this loop, which is 1. Now, once we have set up this equation, now we have to solve this equation. How to solve this? Obviously, we are going to solve the innermost equation first. So I will be a bit quick now because we have already set up this foundation now. So 1 to n, j is going to start from 1 to constant with respect to j and with respect to I both. So I'm going to move this n by 2 out, and by 2 summation I is going to start from 1 to n, j starts from 1 to I square, and remaining stuff is only 1. Right? Now we will solve the inner equation. The inner equation is going to be now n by 2 summation I starts with 1 to n. this is going to be the upper limit, which is I square minus lower limit, which is 1 plus 1. So 1 and 1 is cancelled out, which remains is I square. So now one thing that you have to note here is this I square is not constant with respect to I. This is there. So now what should I do now? I will obviously use one of the formula to solve this sum equation, which is this one, right? How to find it? Let's get back and see where is my formula sheet, and we can, when you will practice, you will figure it out. So this is going to say, if you are going to have n square, I square, you are going to have n into n plus 1 into 2n n into n plus 1 into 2n plus 1 divided by 6. That's what we have got. And now if you can actually solve it using the algebra. But my concern right now is I do not actually need to solve it in detail, because I have to ignore all the constant. And what I have to consider is the higher order polynomial. That I can figure it out here. Like, for example, I can see 1, 2, 3, and 4 n's are being multiplied with each other. Whatever is the constant, I don't care. Whatever is rest of the terms, I don't care. The only thing is what would be the higher order polynomial here, which would be the O of n to the power of 4, right? Why? Because 1, 2, 3, and 4 n's are being multiplied, which turns out to be the n to the power of 4. So I can say that this algorithm behaves O of n to the power of 4 time. I mean, this take maximum time. This is the worst case complexity, or worst, or the maximum time taken by this algorithm. Now you can observe that here. So we were having 3 loops. So it is not n cubed. It's going to be n to the power of 4. Again, most of the time it is true that 3 loops are n cubed, but it's not always true. We have seen in the previous example, it is n square. In this example, it is n power 4. So we have to be careful. We have to solve it before making a final decision. Let's do some more exercises. Let's say, for example, this one. So we are having a loop here. This is a special, important one to understand. In all previous example, the increment was plus plus, right? You can see increment was plus plus. Increment was plus plus. In this loop, the increment is not in the plus. Previously, the jump was 1. I was 1, 2, 3, 4, 5, 6, 7, 8, and so on. But here I is being multiplied with 2. So how can I set up the sum equation now? It's really hard to set up the sum equation in this case. So what I can do is I have to make some observation, like how I is being increased. First of all, I will start from 1. Then I will be multiplied with 2, I will become 2. Then I will multiply with 2, which will become 4. Then I will multiply with 2, will become 8. Then I will multiply with 2, will become 16. So on up to n, right? So what I can say is I can observe something from here, that the pattern in which it is growing, the loop is growing, loop is executing is in terms of 2 power 0. I can write it 2 power 1. I can write it 2 square. I can write it 2 to the power of cube, 2 to the power of 4, so on. And by the time it reaches to n, it would have some power 2 to the power of k, right? So I'm going to start it from 0, 1, 2, 3, 4 up to k. By the time it reaches n, there would be some power which is k. Now my job is to find out what would be the value of k when it reaches to n. What does that mean? Is it means when when my loop will reach to the 2 to the power of k would definitely be reached to the power of n. Oh, sorry, equal to n, right? When my loop will terminate, when it reaches to n, there should be some 2 to the power of k. That now I can simply find out. Now I have figured it out. I can simply apply logarithmic on both sides. So if you apply log on both sides, 2 to the power of k is equal to log n. Now you can simply know that you know the logarithmic rules. So k is going to be out. Whatever is the power, you are going to take it out. So this can become k log 2 base 2, right? Obviously, this is also base 2 on the other hand side as well. Log base 2, which is what the remaining is nothing. So by means, what I'm going to say is if it is 2 to the power of k is equal to n, we can apply log on both sides. We can apply log, this remains as 2 only, right? So why? Because it's super power of 1. Okay, so this is 1. 2 to the power of 1, you taken okay, we have taken k out, k move out, so it's 1. So which is going to be log of 2 base n, base 2n. So this is going to be 1 now. So this whole is 1 with respect to the definition of the log. So k is now equal to log n base 2. So I can say that this algorithm is order of log n base 2. Right? That's how we are going to find out the complexity of such non-recursive algorithm with the loops, where we have jump in terms of multiplication instead of in terms of the addition or subtraction. Okay. Now, if you have, once again, if you have addition or subtraction, you are going to make a jump of 1. Either in case of increment or decrement, you will set up, you will simply say, you will set up the sum equation, like summation I start from this and that and so on. But if you have multiplication factor or division, you can't do so. Then you have to follow this method where you have to find out in what power of, what would be the power of 2 when this loop will stop. And then you have to say, and this can only happen if it is being multiplied with 2. What if I is being multiplied with 3? Then of course it is going to increase. The loop is incrementing in terms of in the power of 3. So then I have to set up 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, and so on, 3 to the power of n. In that case, it is going to be O of log n base 3, right? So if it is I multiplied with 4, then it is going to be log n base power base 4. If it is 5, whatever the number is being multiplied, that will become the base of the logarithm, right? That's how we are going to compute such type of algorithms, the complexity of such algorithms. Let's take some more example. For example, this one. See, what we can do here is, let's say we have one loop here. We have a loop here, say this one, right? So let's set up the sum equation. So I is going to start from n by 2 up to n. Okay, the inner loop is going to start from 1. J is going to start from 1 to n by 2, right? Until n by 2. The innermost loop is going to start from 1 to n. So I can say k is going to start from 1 to n. And whatever we are being performed here is a constant terminology, so which is 1. Now we can set up, we can solve the sum equations. It's simple. We can solve the innermost first. So summation I is going to start from n by 2 to n. J is going to start from 1 to n by 2. And when we solve, this is going to be n, because n minus 1, lower limit is 1, plus 1 is going to be n. Now, if we observe that this n is going to be the constant with respect to j and I both, so I'm going to move this n outside. So n times I starts with n by 2 to n. Next summation j starts from 1 to n by 2. Remaining stuff is 1 only. And now I can solve this inner equation. So how can I do that? Let's see. N into summation I is going to start from n by 2 to n. The inner one is the upper limit, which is n by 2. The lower limit, which is 1 minus 1 plus 1. So 1 and 1 is cancelled out. The remaining stuff is n by 2 only, which again is constant with respect to this I. So I have to move this n by 2 out of this loop as well, this whole summation as well, right? So, okay, we did some mistake here. We performed some mistake here. Sorry, this is not the correct way. The reason why I'm doing this mistake is because this loop, innermost loop, is not going to run for the plus, it's going to increment in terms of 2. So this whole is not valid. Let's just erase this stuff and we can now do it once again. So let's just do it from the scratch. Okay, so let's set up the sum equation once again. So very quickly, I is going to start from n by 2 to 1 to n, and j is going to start from j is going to start from 1 to n by 2, and the innermost loop is going to be k in terms of k times 2, which is something we cannot set up the sum equation. If we cannot set up the sum equation, we have just seen that this is basically log n base 2, right? Why n? Because it is going to end at n, so that's why n. If it is going to end at p, it is log p. If it is going to end at q, it is log q, whatever it is, right? So now this log n is constant with respect to j and I, so I'm going to move it out. Log n base 2, I is going to start from n by 2 to n, j is going to start from 1 to n by 2, and the remaining stuff is 1. So now I can solve the inner equation, which is log n base 2, I is going to start from n by 2 to n, and this j is going to be n by, this is okay, this is going to be n by 2 minus 1 plus 1. This and this is cancelled out. So n by 2 remaining is constant with respect to I. So I am going to move it out. So n by 2 log n base 2. And the remaining is I is going to start from n by 2 to n. And the remaining is 1 only. Now I can solve the remaining the sum equation, which is going to be n by 2 times log n base 2, and this is going to be n, the upper limit is n minus the lower limit, which is n by 2 plus 1 from the formula, right? That's what we are going to get. And now if I solve this one, this is going to be n by 2 log n base 2, and this is going to be 2n minus n plus 2 divided by 2, right? Simply. So now if you can see that, you can actually find it out. Let me just rearrange it. It's going to be n by 2 into 2n minus n is n plus 2 by 2 into log n base 2. So if you compute this, it's going to be something n squared plus something, right? Which is going to be, I only need to have the higher order polynomial while I'm going to write it in terms of the big O. So I can say that this algorithm behaves in big O of n square log n base 2, right? So you cannot ignore log n at this point, because log n is associated with this one, and this falls in the cubic logarithmic class of the algorithms, right? This is how we are going to compute the algorithms. Now let's move next. These are a few more examples that I am going to leave it for you, so you can do them by your own. I will post these PPTs which just have the these questions, so you can just solve it by your own self. So I mean, this is simple. I mean, I can simply figure it out. It is going to be O of n. Why? There is only one loop which is starting from 1 to n. So no matters if it is n minus 1, it's going to be something like this one. I is going to 1 to n minus 1. And what I am going to do, I'm going to perform the comparison. Based on the comparison, this operation will perform. So comparison here, if condition is my basic operation, so which is 1. So when you solve this, it's going to be O of n. The next one is another algorithm to find out the unique elements in an array. So we are going to have two loops here, right? So you can set up the sum equation very quickly. I is going to start from 0 to n minus 2. Then you are going to say, hey, j is going to start from I plus 1 to n minus 1. What you are doing? You are comparing two elements again, which is constant. And now, since there are two loops and they are dependent on each other, it is going to be O of n square. How it is n square? You can actually solve it by your own self. We have done a lot of exercises in our previous slides. Now, one more. Here we are going to have three loops. So it turns out to be the n cube. Let's see, I is going to start from 1 to n minus 1. Then j is going to start from 0 to n minus 1. Then k is going to start from 0 to n minus 1, right? And what we are performing here is sum operation, multiplication, addition, assignment. All are the constants, so I'm going to do it 1. So you can solve it. It should be, I mean, you can test your own answer n to n cube. It should be n cube, right? So you can just now follow the same steps that we have done in previous few minutes. Okay. One more again, it's going to be the 3 loops. Hopefully, I mean, this is again surely is the n cube. You can set up some equation. I is going to start from 0 to n minus 2. Then you can say j is going to start from I plus 1 to n minus 2. K is going to start from 1 to n. And you are performing division, multiplication, subtraction, assignment. All are the constant operation in one time. Now, you have to verify that whether it is O of n cube or not, because we have already seen that by just looking at the 3 loops, you cannot decide whether it is cubic or not. But you have to solve this some equation to figure out whether it is really the cubic or not, the quadratic or not, or whatever class it falls or not. That's how we are going to analyze the non-recursive algorithm. So in this video, we have seen how to analyze algorithms which are non-recursive, which involve loops, specifically the for loops. In the next video, I will talk about how to analyze recursive algorithms. All right, see you then.